All right. And is the screen also visible?
Yes, sir.
All right. Open. All right. So this is what we were doing last time. We started the topic of turning effect of forces, and we discussed what a turning effect of a force really means and how can we quantify this turning effect of a force as well. And that's where we talked about moments, and we saw how is moments is a quantity. It's a quantity called moment, and it's used to quantify the turning effect of a force. We saw that for a moment of a force is acts about some point, and that point was called a pivoting point, which is a point where about which that particular point a body is going to perform a rotation. And then moment of that force is simply about that point, which is equal to the force multiplied by the perpendicular distance from that force, right? So that's your moment. And we talked about an example to understand the idea of moments. We talked about multiple examples. One of them was how you can imagine holding a school bag closer to you and further away from you, and how the turning effect of the force changes, which essentially would mean that the moment of that force has changed. And that is simply known as the moment of force, right? So moment essentially enhances the effect of a force. And we saw that to describe a moment of a force of a system, you need that particular force and you need the perpendicular distance from that pivoting point. On that pivoting point, you can also draw a line of action, which is known as line of action. It's a line about which the body is going to rotate. All right. So that's what we talked about. And here we talked about an example where we saw what does it mean for a moment to be clockwise or an anti-clockwise moment. So any questions from this particular part of the lecture that we had covered?
No questions.
No, sir. No questions. All right. Okay. So then let's move on to the next page. Let me get rid of this thing. All right. So now if you don't have any questions, let me try to write down a problem and let's try solving that problem, right? It has to do with the moments of a force. So suppose you're holding a rod. So let me write over here that this is an example problem. And okay, I'm going to draw a thick rod. This is a particular rod and you are holding it from one end. So suppose the pivoting point is over here. So essentially you can imagine that you have curled your fingers around this thing, right? And you're holding it from this point. So you're just holding the rod. And now let's say that you attach a weight to this rod. Suppose this rod is acting as a meter rule, and this is a meter rule. Suppose it is at a 50 centimeter mark over here, and this point is 0 centimeters, right? So you start reading in this direction, right? In this direction. All right. So suppose I attach a weight. Now the question is, where do I attach this weight? Suppose I'm attaching it at this mark, which is 15 centimeters. And here there's some weight that hangs downwards. So if it's hanging downwards, its free body diagram will look something like this, which this is, suppose it's suppose the weight is 0.5 kilograms. That means it would be almost 5 newtons. Right? Now, suppose that your hand is approximately 10 centimeters, then this mark would be a 40 centimeter mark on this ruler. Right? And now let's state the problem. The problem is that I have placed this weight on this meter rule while I'm holding it, pivoting it at this end. So if I'm holding the meter rule at this end, it means that I have a pivoting point at this end. And the question is that I have to tell the moment about this point, which is the 40 centimeter mark, where you can imagine that your thumb rests on this point. Right? So that's the question. You have to determine the moment of this force, which is the weight of this object, about the 40 centimeter mark. So what would be the first thing that you should be doing? It's also important to note, you will see this written in your questions, that the mass of this ruler is negligible. Can anybody tell me why is that an important assumption that we have to make? Why do we say that why before I solve this problem, I assume that the mass of this ruler is negligible?
It means that the mass of the ruler will not affect the answer.
It will not affect the answer. You can imagine a situation that the ruler is so light compared to this weight that even if I were to include the mass of this ruler and then do my calculations, the effect that it would have on the final result would be in terms of 0.000 something. And we can, for our purposes, ignore that, right?
Yeah,
that
yes.
amount of difference is negligible. All right. So is there any more question? I think you were asking a question. Are you Muiz or Taha?
Taha.
I consider you both the same. Okay, Taha. All right. So were you asking a question as well?
For the unit of movement, is it Newton meters?
Yeah, exactly. Right. It's Newton meters, right? Because we know that moment, if I represent it with m, we defined it as the product of the force times the distance that is perpendicular to that force. And we know that the units for force is newtons and the units for distance is meters. These are the SI units of force. Or you can write them as kilograms meters per second squared times meters, which would be kilograms meters squared per second squared. So these are units of moment, right? All right, so can anybody tell me how will I solve this problem? I have to compute the moment of this force that is acting on the ruler because of this weight, which is 5 newtons. I just write it W is equal to 5 newtons, where W is this force or weight about this 40 centimeter mark. What's the first thing that I should figure out? I know the force, right? The force is with me. I can see that clearly. The next thing is, of course, this perpendicular distance. What would be the perpendicular distance for this force about the pivoting point? That's the point that you have to remember. Or about the line of action. So I can draw this thing like this. This is line of action. This is that line about which this ruler is going to rotate in this particular direction. Right? So the first thing that I need to figure out is this perpendicular distance from the force to the pivoting point. Can anyone tell me how would I do that?
You can subtract the 50 meters by 15.
Can you repeat that again and just look at the diagram, and you're almost close. There's just you have to compute the moment about this 40 centimeter mark. And I drew this pivot like this. So the pivot is really your hand, and we're considering this thumb to be the pivot, right?
Yes. So 40 is subtracted by 15, that's 25.
Perfect, right? So perfect. So what distance is this? If I subtract 40, if I subtract 15 from 40 centimeters, What
25
distance?
25
25.
centimeters.
What is this distance?
Centimeters.
The perpendicular distance, right?
Yes.
So this is the perpendicular distance. This is the distance that I would be using in my calculation if I want to compute the moment about this mark. Is everyone following along?
Yes.
Yes.
All right. If there is any question, I keep on repeating this again and again. Feel free to stop me in the middle. I wouldn't mind that. Ask your question, and then once it's clear, then we can move forward, right? So always make sure that your questions are clear in your head. All right. So with that, this is the distance, and we talked about the force. The force is the weight in this example, and that force is given to us. It's 5 newtons. Now, if I come back to this expression, I have essentially figured out the d perpendicular. I have the force. Now, finding moment is a matter of mathematics, and that's just the force is 5 newtons multiplied by 0.25 meters. Remember to convert this into meters, because if you're using the units for force as newtons, right? So this would be, well, if you do the math, I think this gives you 1.25 Newton meters. The question is, we said that moments is a vector. Now, giving you 1.25 is just a number. I want you to tell me what would be the direction of this moment. I'll give you a hint. It would be either clockwise or anti-clockwise.
I think clockwise.
Clockwise.
You think clockwise? Can any both of you, any one of you, volunteer to explain why do you think that it would be clockwise?
As the weight is downwards towards the ground, and that's clockwise.
Yeah, so you can think in terms of that as well. What about, I think the other person is Hassan or Hassan?
Yes, sir. The
You also said clockwise, right?
positive. It's positive 1.25 Newton meters. So we usually define clockwise as the positive direction for moment.
Okay, all right. So, okay, don't think in terms of that though, because it's a completely matter of your choice whether you say positive is clockwise or positive is anti-clockwise. You can change that. That's not something that nature has chosen by herself. It's something that you're defining. Think in terms of how would this weight cause this rotation about the pivoting point. You can imagine that the weight is downwards, and the net moment is whatever it is, 1.25 Newton meters. It's going to produce a rotation in this particular way, right? Because it's downward, so it's going to make this meter rule bend downwards, or in other words, not really bend, but rotate downwards in this direction overall. And that rotation would look something like this. And this rotation is known as a clockwise rotation for very simple purposes, right? So that's why it would be a clockwise rotation. I hope that's clear for everyone. Even everyone is following along. There are only 2 people talking right now. I want everyone to be telling me if they're following along, so that no one gets left behind. Really, that's the goal, right?
Yes, sir.
Okay. All right. Okay, so we all understand now that the moment would be 1.25 Newton meters, and it would be in the clockwise direction. All right, wonderful. How about now in the same problem, let's change the design of the problem simply by saying that let's move this weight a bit, a bit further away from the pivoting point. So we can, if I draw the same thing very quickly over here again, then this is the pivoting point. This is the rule. This is 50 centimeter, and the pivot is around about, you can say this is 40 centimeters. This was the pivot, and the weight. Now let's move it. Before we saw that the weight was at a 15 centimeter mark. Let's move it further away from the pivot. Let's move it to suppose a 5 centimeter mark. Now that's where the weight hangs. Okay, all right. Without any calculations, can anyone tell me where, in which diagram, in which situation would the turning effect of a force be felt more strongly without any calculations, just by using the
in the
concept?
second situation.
Sorry,
In the
can you
second
repeat?
situation, because in the second
In the second.
situation, because the distance from the pivot is more.
Right. So it's the perpendicular distance has increased, right? So if we know that the moment is force times the perpendicular distance, and because the perpendicular distance from the pivoting point, which is this distance, has now increased as I move the object further away from the pivoting point, then D has increased. And if I multiply the same force with a larger number, the moment now would be greater than 1.25 Newton meters, which was the moment previously, as you can see over here. And let me figure out what would the moment be. The moment now would be, I think, the force is 5 and it's at 5 centimeter mark. So 40 minus 5, that would be around about 1.75 Newton meters, right? This is the new moment when you do the calculation, force times the perpendicular distance. And this moment in its value is also greater than 1.25. And that essentially means the more the moment is, the more the turning effect of a force would be felt. And the reason for that is, why did we define moment in the first place? We define moment so that we can quantify the turning effect of a force, right? So having a larger number for moment would mean having more turning effect of a force. Hopefully that clears the whole idea of moments for everyone. Is it okay? Is it clear?
Yes, clear.
Yes, sir.
Okay, wonderful. Right. So now let's quickly summarize things that we have studied so far, and then we'll move on to, we'll talk slightly, well, whatever we have talked about using this clockwise and anti-clockwise. There is a name for this thing, and it's known as a principle of moments, where we can completely define what does it mean by clockwise and anti-clockwise moments, and how does that relate to a system which is in equilibrium. Does everybody understand the idea of equilibrium?
Yes.
Right now, there are two kinds of equilibrium, really, and actually let's move on to that slowly as we come to that topic. First, let me summarize the things that we have studied so far, right? So quickly I'll give a summary of whatever we have done so far. uh, First of all, one of the main things that we saw was to quantify a turning effect. We use the idea of moment. Turning effect is a physical thing that is happening. Moment is just a physical quantity assigned to that physical thing that is happening. Just exactly in the same way as we defined for a push or a pull, we know that physically when you can push or pull something, but in physics language, you define a physical quantity for that, and that's force, right? In the same way, we quantify turning effect of a force with a moment, right? So that's the first thing that we saw. Now, second thing comes from these things, and it states that if I apply a force on a body, it can produce a turning effect. It can produce a turning effect on that body. It can cause the body to rotate about what is called a pivot, right? And that takes us to the second thing, that what is a pivot? We saw slightly in a bit of detail that a pivoting point, I'll summarize it by just saying that it's a point about which a body is going to perform rotation. Point about which rotation occurs, right? So this is ROT, just a shorthand for rotation. All right, so then we defined moment, and we said that mathematically you can write down a moment as a force that acts on a system multiplied by the perpendicular distance from the pivot of that force. That's how we define moment. And the SI units of moments was dictated by, I think, Taha or Muiz. They said that it's Newton meters, right? And that's true. And the final thing about moments that you should know by now is that it is a vector. The nature of moments is a vector nature, and it can have two possible directions, either clockwise or anti-clockwise. So all these points that I have written down, before we move forward, all of these should be clear. Are they clear?
Yes.
Yes.
Yes,
Okay, perfect. So now we can move on to the next of moments.
Sir, can you go up a little? I still need to write the summaries.
Oh, you're noting these things down? Okay.
Yeah.
That's all right. Sure, go ahead. But I also share these notes with you all in the group, so you can always have. Just if I forget to share the notes, if you want the notes if you're like we don't have the notes yet, just message on the group or personal message me, and I'll share the notes in the group if I forgot to share them.
Okay.
So just remind me. Sometimes I can be a bit forgetful. You'll have to excuse me for that.
Okay, sir.
Okay, so let me know when once you're done. But I think you can see the summary, and we can talk about the principle of moments.
Yes.
So principle of moments, we need to talk about this so that we can assign this rotation to equilibrium, right? So we want to assign rotation to equilibrium, meaning I want to see, we all are aware of this thing, that if I have a system and suppose I have a force that acts in this direction and a force that acts in this direction, and the force is 2 newtons, and there is no force upwards or downwards. In this particular case, can I say that this is in equilibrium?
Yes, because it will keep moving at a constant speed.
Right. So yeah, now that means that if it was stationary, then it would be stationary. If it was moving, it would keep moving without changing its speed. And the reason for that is because the resultant force on this system, if I take the front force in this direction to be plus, so this would be plus 2 newtons, automatically the opposite direction to that would be a negative 2 newtons, and the resultant is 0 newtons. Hence, there is no resultant force that acts on the system, and I can state that the system is in equilibrium. But hold on, I have to be careful. the system is partially in equilibrium, there is another condition for equilibrium, and that is the condition that we want to talk about, and we'll talk about very soon. It's how can I relate rotational motion with equilibrium, right? So rotation also plays a vital role in equilibrium. You cannot ignore it. You have to cater for that in your conceptual understanding. So if I talk about principle of moments, have you ever wondered how is it possible that people, and if you go to a shop to buy vegetables or fruits, they use this thing which is called a beam balance to measure the mass of, you know, whatever you're buying.
Yes.
Right. So I can draw a free body diagram for that. I'm not going to draw an accurate drawing because I'm not an artist, but I'm going to try to draw this free body diagram. You notice that at one end of the balance, there is always a fixed mass. It might be 5 grams, 1 kilogram, 5 kilograms, or whatever, right? But they have this standard masses. I'm going to draw it like this circle because that's how they have them. And suppose it's whatever, right? But it's a standard mass. It's a mass that has been already measured, and it is written on top of this thing that maybe it's 5 kilograms, for example. And on the other end, they put whatever you bought, maybe a bunch of apples, right? So many of these apples. So that's what they placed on this side. And when the beam is balanced, that's when you can say that the mass of these apples and the mass of this standard mass is exactly equal. And so you can say that the mass of the apples is 5 kilograms. Everybody agrees with that?
Yes.
All right. So if this is balanced, then let's call this some M1, then M1 is equal to this 5 kilograms. Imagine if 5 kilograms tipped downwards, which would essentially mean that the apples would move upwards. What would that state comparing these two masses? What would that mean if I compare the two masses? If 5 kilograms tipped downwards?
That
The
means
apples are lighter than 5 kilograms.
The apples would be lighter than 5 kilograms. And the other way around, if the apples tip downward, means the apples are heavier compared to the mass of 5 kilograms. So far, is this thing clear? That's how we measure
Yes.
the mass of objects using this beam balance. And that's where the idea of principle of moments comes in. Saying that the principle of moments is telling you when the body is in equilibrium, right? So I'll state that over here. Let me state the principle of moments. It goes something like that. When a body is in equilibrium, EQ stands for equilibrium. This implies that sum of all the moments that are anti-clockwise is equal to sum of all the moments that are clockwise. About, the important thing is all of this about the same pivoting point, right? So I used some symbolic notations. Is it understandable for everyone? Do you understand that this notation means sum? And it's just saying that the sum of the moments that are anti-clockwise, all of such moments are equal to all the moments that are clockwise. Sum of all the moments that is.
Yes, I understand.
Once that's the case, then the second, yeah, okay. All right, so then the second condition of equilibrium has been developed, and that this is known as the second condition of equilibrium, right? Where there is no net rotation of a system. So there are two types of equilibriums then. Before I go on to that, let me just take your attendance because I don't know when the meeting will end. So there are some people. Let me just take a screenshot of this thing.
Sir,
right,
it says the
so-
meeting will end in 6 minutes.
Yeah, the meeting will end in 6 minutes. So we'll talk about this principle of moments. We have talked about this. Let me just talk about the conditions of equilibrium. And then the last topic remaining would be the center of gravity. How can I check for stability of a system? And then we'd be done with this chapter as well. Right, and the next topic would hopefully be about energy, and that's a very interesting topic where we'll see lots of interesting things. And one very important law of physics would be discussed in that chapter. Anyways, coming back to this thing, the thing I want to end this lecture with is the conditions for equilibrium. And the conditions for equilibrium, one of the conditions that again I explained, which I said that if I have a block and I have a force like this, and suppose the force is same in both the directions, this kind of an equilibrium is known as a translational equilibrium. Translational because it's talking about a linear translation motion. Translation means moving along a line. It could be like this, the line could be like this, the line could also be like this, whatever the direction is. The second condition, which the principle of moments led us to, is known as a rotational equilibrium. And the rotational equilibrium is given this name because obviously if I talk about a system like this, then because of the moments it can rotate. But suppose that it was about to rotate, this is the clockwise rotation, this is the clockwise rotation. And then if the sum of all the moments for a clockwise rotation and an anti-clockwise rotation are same, then there would be no rotation. Suppose if this was the pivot, there would be no rotation of the system, and the system would be told to be in a rotational equilibrium as well. Finally, we can say that a complete equilibrium means for a system to be in a complete equilibrium, it has to satisfy 1 and 2 together, meaning it has to be in both the translational equilibrium and the rotational equilibrium. And that's when my system is in its entire complete equilibrium. There is no other equilibrium, right? Only these two equilibriums, and if these two are satisfied, then the system is in complete equilibrium. So is the idea of equilibrium clear
Yes.
to everyone? All right. So in the next class, we'll talk about the center of mass and stability. We might even look at some of the examples for this equilibrium, as I don't think we can do that right now because there's only less than 3 minutes remaining. So in the next one, we'll end this topic as well, and we'll move on to the work, energy, and whatever it's called. Are you satisfied with the pace right now? I've tried to increase it slightly. I don't know if it has made any difference in your frame, but let me know. Is the pace okay, or should I try to increase it even more?
Okay, sir.
Try to increase it to even more.
Try to increase it even more from Taha and Movies. I think both of them. How about the other rest of the class?
Yes, I think it's fine.
Okay. Can you all, before in the remaining time, just let me know? You can either type this in chat if you're too shy to speak up, but please let me know when are you all giving your exams, the exams for Cambridge? October, November, or May, June? Just let me know.
October,
You can
November.
type it in chat. Okay, or you're all right. So I would prefer if you could type it in chat, so I can note it from there, and then look at things from that perspective. You can just type May or October, so I'll know which session are you all going. Okay, we have one for October, November, May, June, October. All right, keep going. How about the rest of the class? May, June, October, November. So right now we kind of have a balance between the two. So we can kind of say that this class is in equilibrium. Okay, so there's still a lot more